finding limits is involving what you might remember as the Squeeze theorem. It's a very popular theorem to be skipped over in Calc 1. It's like, oh, hand waving, here's the Squeeze theorem. You get it, right? Okay, moving on. That's kind of like what we're dealing with in this class, is that everybody should know the Squeeze theorem, but hardly anybody really has any kind of good experience with it. Prove the following limit exists and is equal to 0. All right. And we're using the Squeeze theorem to do that. All right. Now, if you look at the relationship, it's kind of weird. You have that whole mathematical statement that doesn't really explain anything. It comes down to, what we're familiar with from in the past, that if you have two functions that are approaching one another, right? If they're approaching one another, they're going to have the same limit. I can give you a quick example on the Desmos calculator. Let's say we have y equals 1 over x and y equals negative 1 over x. And I'm just looking at this for positive values of x. You can see that it's squeezing in between them the x-axis. But I could have some other function. It really doesn't matter what it is. Let's say I want something smaller. Let's say 1 over x plus 2. Right, that function is in between the other two functions. And maybe I don't know what the limit is as x approaches infinity of 1 over x plus 2. But I do know that the limit as x approaches infinity of 1 over x and also negative 1 over x, they both go to 0. Because the 1 over x plus 2 is squeezed in between those other two functions, wherever they're going, that third function must also go. All right, so that's the essence of the Squeeze theorem. We just need to apply that to multivariable functions. All right, so what we're going to do is we're just going to kind of go with something that we know is a true statement and just kind of build outward from there. All right, so let's say, for example, that I'm only interested in the denominator. You can't just steal a denominator and make it its own thing, and it's not a fraction anymore. But I can kind of take the parent function out of there. And I'll just call this 1 over x squared plus y squared. All right. Now that function, well, I'm writing it as an expression, but it represents a function, is in terms of two variables, so I can't graph it on Desmos. I could take a look at it on GeoGebra, but it's going to be messy anyway, so there's no point, right? What I want to do is establish a relationship, something that I know is true. Like, for example, just thinking in terms of fractional values. Let's say you have the number 1/2. All right, 1/2 we know is valued at 0.5. Very, very simple. Now, if I want to get a value that I know is going to be less than 1/2, so a smaller value, I can do a couple of things, but one of those things would be just to increase my denominator. All right, that'll guarantee me a smaller value. All right, I could also go the other way. If I want to get a bigger value, I can decrease the denominator. All right, so if I take away something from the denominator, I can get a bigger valued fraction. So that's what I'm going to do here. I'm going to say, well, I know that this fraction has to be less than 1 over x squared. Right? You pick whatever numbers you want, plug it in, you'll see it's true. Right? You're dividing by less. Y squared is always going to be positive. You're adding a positive number that is guaranteeing that other fraction is going to be smaller. Right? But what we can do is we could say that the absolute value of this is less than 1 over. If we really want the parent function out of this, we would look at the absolute value of it. to ignore any possibility of negatives, although there's no way you can get a negative out of this anyway, all right? But what that does is it gives us a natural boundary on the low side. This yields -1 over x squared is less than the middle function, which is going to be less than this guy. It's still not what we're looking for, but we're getting closer. Now what I want to do is I want to incorporate the numerator. I want to bring that back to the party. All right, so what we can do is multiply this entire inequality, this compound inequality, by x squared y. All right, and when you clean it up, you see a lot of beautiful things start happening. And let me make that 2 look more 2-like. All right, and I'm going to also shrink this down a little bit. So you get -y is less than x squared y over the x squared plus y squared, which is less than a straight up y. All right, so that relationship we know is true because we started off with an expression that we knew is true, or a relationship that we knew is true, and we built off of there using appropriate mathematical approaches. So now what I can do is the beauty of digital inking. Tuck a little limit in front of each piece. If you have the foresight, then you write it with the space to begin with. But we would then find the limit as xy approaches 0, 0 for each piece. Just making sure it's the right values. Let me move this over a little bit more. And then I could apply my limit. See, the x ends up being irrelevant. So all I'm going to do is replace my y's with zeros. You see on the low end and on the high end, we're looking at 0, which tells me that this limit is trapped between two functions that are approaching 0, which means the function itself also has to be approaching 0. And that's really all there is to it, except, you know, there's a lot going on, but it's a prescribed approach. If you look at number 5, you see, okay, well, this just seems to be a beefier version of what we just did. All right, so you start off with a known relationship. We have 1 over x squared minus, 1 over x minus 1 squared. So really this denominator under a 1. That's going to be less than, I just want to know a fraction that, a fractional value that it's going to be less than. Now, before I said it was less than 1 over x squared, I could have said it was less than 1 over y squared. You can go either way with that. You can go with the simpler function. The thing is, it's not always going to clean up nicely depending on which one you go for. But you can kind of pick your battles. It really doesn't make a difference. But yeah, like ideally you'd grab the simpler of the two and see how it plays out. All right. So I could say that this is less than 1 over y squared, and I'll rewrite it, or the whole thing we could look at it as 1 over x minus 1 squared. Either way, it's going to be equivalent. All right. I'm going to go with the simpler one, though. That's kind of the way we want to do things. If possible. We'll find out in a minute if it is. All right, we run through multiplying by the numerator. All right, so that whole numerator is going to get multiplied through. All right, now the next part of the process in your mind, you want to play it out and you say, okay, is that going to get the job done? Because before you write any more, you got to make the strategic decision to say, all right, this is the right path to be going down, or it's not. If I multiply each part of this fraction, or this inequality, by the numerator of that fraction, yeah, it'll make the middle what I want it to be, but it's not going to make the outside portions what I want them to be. All right, which is something simpler. All right, always something simpler. All right, so this was a good thought because it's a simpler form, but it ends up being not the right one. So big old X through that one, and I'll shrink it down. But we had to try it, because what if it did work? It would have saved us some time, but alas, not the case. All right, so we go with the other possibility. I'm going to shrink it down a little bit. All right, so now when I multiply through with that x minus 1 squared times the natural log of x, see, we get a lot of nice cancellations. All right, on the low end, it ends up being negative ln of x. In the middle, it is what it is, a monster of an expression. And on the high end, we're also looking at an ln of x. So again, here, the foresight to leave the space so I don't have to move later. Okay. So limit as x, y approaches 1, 0. So we're plugging in a 1 for the x's. In both cases, natural log of 1 is equal to 0. We're going to get 0 on both bounds, which is good because that's what we're going for. And so we would get our conclusion that this limit itself is equal to 0. All right. Putting together concepts involving limits and domain gets us to the idea of continuity. So number 6, they're asking us to find all points where a function is continuous. So what I would want to do first is determine if there are any points where the function is undefined. Right? So, or imaginary, but in this case, imaginary is irrelevant. So I have x squared minus y. I'm going to set that equal to 0. And when I solve, I get y equals x squared. All right. So these values would have to be excluded from the set. Anything in the form of y equals x squared, right? Or any variation of that, right? So those are the bad values. So what I would want to do here is make sure that the function exists for all other possible values. Now, we're not going to test all of them, but what I'm going to do is verify that the limit does not exist for this relationship. All right. So what we can do, we can handle this a couple of different ways, but typically we're looking at the limit as x, y approaches some a, b value of f of x comma y, that's going to be equal to f of a comma b. All right. That shows that a function is continuous. So what I would do is I would use that information and this new exclusion and see if I can modify. All right. So we know y is equal to x squared, so I could rewrite this limit as x comma y is approaching, instead of a, b, because a is the x value and b is the y value, I would want the x and y values to be in the form of y equals x squared. All right, so here's my a. I would call this a squared. All right, and that's of f of x comma y. So f of x comma y is x over x squared minus y. Let's go in for the x's, and this goes in for the y. So I'd be looking at a over, that's not horizontal, also not horizontal, a squared minus a squared. All right, which is a over 0, which is undefined. All right, so it's undefined, but it's certainly not equal to f of ab. All right, so what we're looking at here is something that's not continuous because it doesn't satisfy that relationship. All right, so I just want to kind of clean this up a little bit. I'll chuck this up here or down here, or well, I'll chuck it up here for a second. I'll move this over. And I'll put this down here because I want to use this. I just don't feel like rewriting it and copy and pasting it. Right. So since the limit as x approaches y, x approaches y, x comma y approaches a comma b of f of x comma y is not equal to f of a comma b, or y equals x squared, the function is not continuous on that path. All right, but I do have to address continuity. I got to answer the question that's being asked. I'm going to shrink it down, a little shrinky dinky here. Shrinky dinky doodle. So it's continuous. So we want to address where it is continuous. So it's continuous on x comma y such that y is not equal to x squared. All right, so all that stuff that preceded it was a proof. It was proving, but you know, we did it first algebra 1 style. We came up with the excluded values just by setting the denominator equal to 0, but then we needed to verify that it wasn't going to lead to continuity. And once we did that, we had to make a formal statement as to what is continuous and what isn't.